At 2 a.m., when you prompt an AI to generate like a cyberpunk cathedral made of circuit boards, it really feels like it's just instantly conjuring art from thin air.
Oh, yeah. I mean, 3 seconds later, there it is on your monitor. A literal masterpiece.
Right. And it is incredibly tempting to view that output as some sort of digital magic. But if you were sitting there staring at your code editor, you know better.
You know it's just math.
Exactly. The system is actually running the ultimate undo function on pure mathematical static.
And the paradox of that architecture is just fascinating. Like, to teach a neural network how to build a coherent picture, researchers first had to teach it how to systematically destroy one.
Yeah, so our mission for this deep dive is to tear down that architecture. We are stepping away from the awe of generative AI to really deconstruct the algorithms, the data structures, and the mental models that make diffusion models actually work.
Right, stripping away the magic.
Exactly. So whether you are listening to this on a late-night commute or maybe you're just waiting on a massive container to build in the background, we're going to look under the hood at the actual mechanics of image generation.
Because once you map out the sequence of operations, that whole illusion of the machine, knowing how to paint, it just vanishes. What remains is a highly optimized pipeline of tensor math.
Totally. So let's start with that paradox of destruction. Because reading through the research papers on the forward process, it requires a bit of a perspective shift, right?
Yeah, it really does.
The training does not start with a blank canvas. It actually starts with a pristine, high-resolution photograph.
Right, and then the system applies a Markov chain of Gaussian noise. So over a series of steps, and we're talking often 1,000 or more steps, the model injects a calculated amount of random static into the image tensor.
1,000 steps of just adding noise.
Exactly. And a Markov chain basically just means that each step of destruction only depends on the state of the image in the immediately preceding step.
Okay, so if you take a really crisp picture of a mountain, right? At step 1, you perturb the pixel values slightly based on a normal distribution. So it looks like a very light grain.
Just a little dusty. Yeah.
Right. But by step 1,000, the spatial structure of the mountain is entirely gone. Like the matrix is just pure isotropic Gaussian noise. It looks exactly like television static.
But the crucial element of that forward process is the variance schedule.
Right. It's not random.
Exactly. The noise isn't just applied haphazardly. The system scales the variance at every single step, meaning the math tracks the exact statistical distribution of the noise being added.
And I found myself struggling with this concept initially, honestly. Because if you have completely scrambled the data into pure noise, how can a neural network possibly learn to reverse it?
It seems impossible.
It does. It feels like trying to unburn a piece of paper by just looking at a pile of ash.
Well, attempting to go from pure ash to paper in one leap is impossible. The neural network cannot reconstruct a mountain from pure static in a single forward pass.
Right, that would be magic.
Exactly. And that is where the step-by-step parameterization is the absolute genius of the diffusion model. We only ask the network to predict a microscopic fraction of the destruction at a time.
Ah, okay. The reverse process.
Yeah.
So instead of asking the model to just draw a mountain, we hand the neural network an image that is, say, at noise step 850.
Right.
The network analyzes it, and its only job is to output a tensor that predicts the specific noise that was added during step 850.
Just that one step. Then, by subtracting that predicted noise tensor from the image, we step backwards to step 849. So the model evaluates the impossible creative task of, making art as thousands of tiny, solvable denoising regressions.
Which means the loss function becomes incredibly straightforward.
Yeah.
The model makes a guess about the noise. We compare it to the actual noise we mathematically added during the forward process, calculate the mean squared error, and backpropagate to update the weights.
Yeah, the training is just learning to map noisy inputs to the noise residuals.
It's so elegant. Over millions of iterations, the neural network just becomes an expert at peeling away static layer by layer.
Right, it sculpts a crisp image out of a random noise matrix.
Now, the underlying math makes total sense to me. But if you are the one paying the cloud infrastructure bill, this logic hits a massive wall when you look at the compute requirement.
Oh, absolutely. The cost is huge.
Let's say we are generating a standard high-definition image. That is a massive array of pixels across 3 color channels. If the model has to run a deep neural network forward past 50 or 100 times on that full pixel matrix to denoise it step by step, the memory overhead would just crash a standard commercial GPU.
Yeah, operating directly in pixel space is computationally exorbitant. I mean, the matrix multiplications required for attention mechanisms, they scale quadratically with the spatial dimensions of the input.
Which is why early diffusion models were incredibly slow, right?
Exactly, for this reason. They were running on raw pixels.
So how are the current models running on consumer hardware in just a few seconds? Because I know the industry didn't just sit around and wait for better silicon.
No, they didn't. The breakthrough was moving the entire denoising process out of pixel space and into what is called a latent
The
space.
latent space.
Yeah, and this relies on an architecture known as a variational autoencoder, or a VAE.
Okay, wait, so is the encoder just aggressively downsampling the image? Like, is it passing it through pooling layers to create a low-resolution thumbnail, doing the math on the thumbnail, and then blowing it back up?
Not quite. Downsampling destroys spatial detail. A VAE does something far more sophisticated than that.
Oh, interesting.
The encoder network actually translates the 1024 by 1024 pixel grid into a much smaller, dense, multidimensional representation. It is mapping the mathematical features of the image rather than storing raw RGB values.
Okay, so the tensor shrinks spatially, but it gets deeper in feature channels.
Exactly.
So instead of storing the color of a specific patch of pixels, the latent tensor encodes concepts like sharp edge or gradient lighting or fur texture.
You've got it. The spatial dimensions are often compressed by a factor of 64, which reduces the computational load immensely.
Wow, okay. That reframes the architecture completely. It is very similar to taking a massive repository of raw data, zipping it into a much smaller archive file, applying all of your intensive data transformations to the compressed archive, and then only unzipping the final product when the job is completely done.
That's a perfect analogy. The latent space is your zipped archive. The iterative forward and reverse diffusion processes, the adding and predicting of Gaussian noise, all of that happens entirely inside this compressed mathematical grid.
So the neural network never actually touches a real pixel during the denoising loop.
Never. Not once during the loop. And then once the latent tensor is completely scrubbed of noise, the decoder portion of the VAE steps in.
The unzipping phase.
Right. It takes those denoised mathematical features and projects them back out into a high-resolution pixel space.
And that abstraction is what allows these models to run on a laptop instead of requiring a massive supercomputer cluster.
Exactly. It's an incredible efficiency hack.
Okay, so we have an incredibly efficient denoising engine operating in a compressed space. That completely solves the hardware bottleneck.
Right.
But it leaves a massive gap in the pipeline. If the model is fundamentally just a machine for removing static from a latent tensor, how do we steer it?
Yeah, the steering is the tricky part.
Right, because when I type cyberpunk cathedral into the prompt, how does a string of text actually alter a noise-predicting equation?
To understand that, we have to look at the specific neural network architecture doing the denoising work inside that latent space. And the industry standard here is the UNet.
UNets. I mean, those were originally designed for biomedical image segmentation, if I recall.
Yes, they were.
And they have a very distinct shape.
They do. The architecture downsamples the spatial resolution of the input data into deep, compressed layers to extract features, basically moving down the U shape, and then upsamples it back to the original resolution.
So the bottom of the U forces the network to capture the global context of the image, while the skip connections bridging the downward and upward paths ensure the local high-resolution details aren't lost in that bottleneck.
Exactly. And within those UNet layers, the steering you mentioned is handled by attention mechanisms. Specifically, the network relies on a tag team of self-attention and cross-attention.
Attention mechanisms. Those can get highly abstract when you dive into the tensor queries, keys, and values. What is the functional role of self-attention in this specific context?
So self-attention acts as the internal logic checker for the image tensor itself. As the UNet evaluates a specific patch of latent features on the left side of the image, it calculates attention weights against every other patch in the image.
Oh, to enforce spatial coherence.
Exactly. If the lighting source is established on the top left, self-attention ensures the shadows cast on the bottom right actually align with that source.
That makes sense. The latent tensor is constantly cross-referencing itself to ensure it doesn't build a contradictory scene.
Right. And while the tensor checks its own internal consistency, cross-attention serves as the external bridge. Here, the queries come from the image features, but the keys and values come from your text prompt.
So the features are essentially querying the text embedding. As the UNet processes a patch of the image and tries to determine if a structure should be, say, a solid wall or a window, it reaches out to the text data to check if there are any instructions about stained glass.
Exactly. The text conditioning is injected at multiple resolutions throughout the UNet at every single step of that denoising loop.
Okay, the cross-attention bridge makes sense in theory.
Yeah.
But I was reading that early models still really struggled with this. Even with the text data available, the model would often just ignore the prompt if it found an easier mathematical path to generate, like a high-quality generic landscape.
Yeah, it would default to the path of least resistance. A model heavily conditioned on text can suffer from degraded image quality, while a model with weak conditioning just ignores the user entirely.
So how do they fix that?
The solution to this is a technique called classifier-free guidance.
Oh, I've seen that term. And the math behind classifier-free guidance is surprisingly aggressive, isn't it?
Yeah.
The system doesn't just gently nudge the model toward the text prompt.
No, not at all. It runs two completely separate noise predictions at every single step.
Wait, two separate predictions per step.
Yep, it calculates a conditional prediction using your text prompt and an unconditional prediction using an empty prompt.
So if you visualize those predictions as vectors, the unconditional vector points toward where the model naturally wants to drift, let's say, toward that generic sci-fi building.
Right.
But the conditional vector points toward where you actually want it to go, the cyberpunk cathedral.
Exactly. And then the system subtracts the unconditional vector from the conditional one, calculating the exact difference between them.
Oh, so it finds the mathematical delta between what I would draw without instructions and what I draw with instructions.
You got it.
And then it multiplies that difference by a guidance scale, a value like 7 or 8, and basically forces the denoising process hard in that direction, like yanking the steering wheel.
That's a great way to put it. By extrapolating away from the unconditional prediction, you force the model to amplify the specific features that make your text prompt unique. It is a literal mathematical magnification of the user's intent. That guarantees the final image aligns with the prompt.
Man, the orchestration of these systems is just a masterclass in software architecture. You have a UNet running inside a variational autoencoder's latent space, querying text via cross-attention, and being forced on target by vector extrapolation.
A lot of moving parts.
It is. But for anyone who has followed machine learning over the last decade, the dominance of diffusion feels like an incredibly abrupt pivot. Because not long ago, the entire industry was entirely focused on GAN's generative adversarial networks.
Oh, absolutely. GANs were the undisputed kings of image generation for years.
Right.
The architecture featured a generator creating images and a discriminator acting as a critic, basically trying to classify whether the generator's output was real or fake data.
So two neural networks locked in a zero-sum deathmatch. The generator constantly updates its weights to fool the discriminator, and the discriminator updates to catch the fakes. It is a highly complex min-max optimization problem.
Very complex.
Why did researchers abandon that setup for diffusion?
Well, the adversarial nature of GANs made them notoriously brittle to train. The gradients flowing from the discriminator back to the generator can be highly volatile.
In what way?
If the discriminator learns too quickly and becomes too good at spotting fakes, the generator's gradients just vanish.
Oh, so the generator just stops learning entirely.
Exactly.
It's like trying to teach a junior developer by only returning a fail on their pull request without ever showing them the logs of the syntax errors. They freeze up because there is no clear path to improvement.
That is exactly what happens. And this training instability leads directly to the most catastrophic failure state for generative models, which is mode collapse.
Mode collapse. Now, as an engineer, mode collapse sounds exactly like a system figuring out a cheat code to pass a badly written unit test.
It basically is. The generator's only objective is to fool the discriminator, right?
Right.
Imagine a GAN trained to generate human faces. By random chance, it outputs one specific face with sunglasses, and the discriminator fails to catch it. The generator realizes it has found a guaranteed winning output.
Oh no, so instead of continuing to explore the latent space of all possible human faces, the generator just camps on that single solution.
Yeah.
It just spams the face with sunglasses over and over again because the math rewards it. It collapses to a single mode.
Exactly. The diversity of the model's output drops to near zero. It becomes a one-trick pony. Diffusion models fundamentally bypass this problem because they are not playing an adversarial game at all.
Diffusion is just a simple regression problem.
Exactly. The objective function is merely mean-squared error on the predicted noise. The optimization landscape is predictable, it's convex. The model does not have an opponent to fool. It only has to peel away static across millions of different training images.
And because the model is forced to reconstruct the specific image hidden under the noise at every single training step, it has to map the entire distribution of the dataset.
Right.
It cannot take a shortcut or spam a single face, because the math requires it to learn how to denoise everything from a cat to a cathedral.
That's the beauty of it. The primary trade-off, of course, is inference time. A Jan can produce an image in a single forward pass. Diffusion requires dozens of iterative steps through the UNet.
Which takes longer.
It does. However, the AI community concluded that the massive gains in training stability and output diversity were well worth the extra computational cost.
That makes total sense. And looking at the scale of what we have covered today, there is a really powerful lesson here about structured problem solving. If you are listening to this and trying to debug a complex, unstable system of your own, diffusion models offer an incredible blueprint.
They really do.
The industry did not solve the impossible problem of making a machine creative. They reframed the problem entirely.
Right. By breaking creation down into the highly quantifiable task of predicting noise residuals, moving that workload into a compressed mathematical space to make it hardware viable, and trading an unstable adversarial game for a robust regression objective, they basically unlocked a new era of generative technology.
It's brilliant. We have mapped out the entire pipeline today, from Markov chains of Gaussian noise to the compressed tensors of the VAE latent space, to the self- and cross-attention mechanisms firing inside the UNet.
It is a truly elegant architecture, relying on disparate mathematical techniques layered perfectly to achieve a single goal.
But, as is usually the case in software engineering, solving one mystery in the stack immediately exposes another one just below it.
Oh, always.
We established that the UNet relies on cross-attention to continuously query your text prompt during the denoising loop. The latent features reach out to the text data to guide the generation.
Right, the bridge connecting the visual data and the text data is clearly defined.
But the glaring issue here is that the neural network does not process strings of characters. It does not understand English syntax, and it inherently does not know what a cyberpunk cathedral actually is.
No, it only processes multidimensional matrices.
Exactly. So before that cross-attention bridge can even be utilized, how does the system translate human language into a mathematical tensor that accurately captures the semantic meaning of your prompt?
Well, that translation layer requires an entirely different architecture, relying on contrastive language-image pre-training.
And that is a complex rabbit hole for you to explore the next time you are waiting on a deployment to finish. But the next time you hit enter on a prompt and watch an image materialize on your screen, you'll know exactly the sequence of operations executing under the hood. There is no magic in the machine. It is millions of parameters executing a flawless mathematical undo function on pure static.